Here we have in the new video is nucleophilic addition with HCN in aldehydes and ketones. Basically, aldehydes and ketones are special kind of organic compounds, and you already know the aldehyde carbon have a double bond to the oxygen and a single bond to the hydrogen. So this is in fact the functional group of aldehyde. In the ketones, there will be a C double bond O with two R groups. So aldehyde and ketones also both undergo addition reactions with hydrogen cyanide. Reaction addition with in these reactions, addition of hydrogen cyanide takes place across C double bond O. However, the attack is by nucleophile, not an electrophile. So that's the reason it is a nucleophilic addition. The HCN in this case is in fact generated in situ. In situ means in the reaction vessel by the reaction of the potassium cyanide and dilute sulfuric acid. You can see in this equation this is propanol reacting with HCN, and there is a formation of 2-hydroxybutane-nitrile. Note that the carbon atom has been added to propanol. So 1, 2, 3, 4 carbon atoms now. So here we have 1, 2, 3 carbon atoms. Here we have 1, 2, 3, 4 carbon atoms. So this is a useful reaction for chemists making new compounds, and it increases the length of the carbon chain in the original aldehyde molecule by 1 carbon atom. Hydrolysis of the nitrile group. This is very important to understand that we can hydrolyze the nitrile group into the carboxylic acid. A lot of questions have been asked about this part in P1 and also in the P2. You can also hydrolyze the nitrile group by refluxing with dilute alkali. So you can see here it is we are hydrolyzing with the acid, but we can do the same thing with the alkali as well, like sodium hydroxide. So if that would be the case, then there is the formation of C double bond or COONA. So sodium salt of carboxylic acid can be formed. If you want to produce carboxylic acid, the products are treated with strong acid such as dilute sulfuric acid. Mechanism of nucleophilic addition. So the carbonyl group in aldehyde and ketones is polarized due to high electronegativity of the oxygen atom. The electrons in the C double bond O are drawn nearer to the oxygen atom, giving it a partial negative charge and leaving the carbon atom with a partial positive charge. This makes the carbonyl atom open to attack by the nucleophile such as the cyanide. You can see here this cyanide cause a positive charge in this carbon. Now this carbon, from here the electron transfer to the oxygen, and there is the intermediate formation. The negatively charged intermediate formed in the first step in the mechanism is highly reactive and quickly react with the aqueous H plus ions. The hydrogen ion could be from the HCN, from dilute acid, or from water present in the reaction mixture. This forms 2-hydroxynitrile product, as you can see in the step 2. So this OH react with this one. So we have OH, here we have CN, here we have C, and this CN is regenerated. All aldehyde and ketones form 2-hydroxynitriles when they undergo nucleophilic addition. This is because OH group will always on the adjacent carbon to the nitrile group. However, starting with the aldehyde methanol, the hydroxynitrile formed in its nucleophilic addition with HCN would be called hydroxyethanitrile. In this case, there is no need to insert 2 at the start of its name, as the OH group could only possibly bond to a single carbon next to the nitrile group. Right, now we have a question to understand. Ethanol undergoes addition reaction with HCN in the presence of Cn minus ions, which will identify the type of reaction and the name of the product. So obviously with the ethanols, with the aldehydes, we already know that there is nucleophilic addition, and always there is a formation of, in this case, as this is ethanol, and 1 CN will be going to be added. So there is a formation of 2-hydroxypropanitrile. This reaction show the same thing. So the answer will be C. In this question, the product of the reaction between propanone and hydrogen cyanide is hydrolyzed under acidic conditions. So the formula of the final product you can see here. CO, it is the ketone plus HCN. You can see OH will be added here, CN will be added here. With the help of H plus ion, it will be converted into this one. So Ci3 twice, COOH and COH. So D will be the answer. Okay, here we have another question. Why does SCN add to propanone but not to propene? It's simple. The addition product formed with the propene would not be stable. No, obviously it is incorrect. The propanone is more susceptible to nucleophilic attack because of this reason. You can see here this CN and this CN can add to this ketone. It is possible, but it cannot be added to a propene because in the propene there is no polarization like this. Same is the case with C part and with the D part. Because it's not a radical attack, it is the attack from a nucleophile, only nucleophile. So propanone undergoes nucleophilic addition reaction with HCN due to presence of partial positive charge on the carbon of the carbonyl. This latent deficient carbon suffer nucleophilic attack by the Cn minus. So it is clear. And here we have the end of the video. Thank you very much for watching. See you in the next video. Thank you very much and Allah Hafiz.